Hello, everyone. Good afternoon. Welcome to the opening of the PWF Sudan, the second edition, Expanding Horizons in Physics in Sudan. This time, our workshop is about density functional theory methods and applications. And today we have a special guest. It's a real pleasure for me to introduce Professor Richard Martin, a leading figure in theoretical condensed matter physics, specifically in the field of electronic structure. Professor Martin received his PhD from the University of Chicago and is currently a consulting professor at Stanford University. And he retired from the University of Illinois in 2007. So over the course of his career, he has made fundamental contributions to how we understand and compute the electronic properties of solids. His work that supports much of the modern material science of today. Many of you might know or familiar with his textbook, Electronic Structure, Basic Theory, and Practical Methods, which has become a standard reference for students and researchers alike. His contributions have been widely recognized through a number of research honors. For example, he's a senior research fellow prize from Alexandra Humboldt Foundation and other fellowships. Beyond his research in recent years, Professor Martin has been devoted to advancement of the research opportunities for scientists and researchers in less developed countries, specifically through his work as a chair for International Advisory Committee for the African School for Electronic Structure, Methods and Applications, a well-known school for electronic structure. Please join me in a warm welcoming to Professor Richard Martin. And please, Professor, you can start your presentation. You can share your presentation with us.
Thank you very much.
Okay, I think it's better, yes.
Now, is it working?
Perfect, yes. Now it's perfect, yes.
My apologies.
No, it's fine. It's really fine. Yeah, go ahead.
I use Zoom a good bit, but I do not share often.
Yeah, Zoom is very complicated. It's okay.
Oh, yes, it changes every time.
Exactly. Go ahead.
Okay, now can I say that it's a pleasure and an honor to be introducing this workshop. As you know, I've been involved in the electronic structure methods and applications, a series of workshops for many years now. And I've gotten to know a good many people that are on this screen. And it's a real pleasure to work with you and to thank the organizers, Musa, Fatima, Sarah are the ones I know, but I know the others of you did a great job. So thanks for doing this. So what I want to do is to set the scale for what it is we want to do and to give some of my personal takes on this field. So why do we study material science? It's a computational material science, I should say. So advances in the theory and computation have reached the point where we can really make accurate predictions for many important problems. That is, you can make a real difference. When I started this work, theory was essentially always models and very simple approaches. And now it's a situation is completely different. Experimentalists actually pay attention, and people work with theory along with the experiments. So it's become a completely different field from years ago. So at this field, there's active research in fundamental physics, forefront work in chemistry, material science, and other fields, and applications to real problems. And at the same time, there's being developing new computational methods that make it more and more powerful. So this field is particularly useful and great to be a part of because it's an active community of researchers bringing together all these different problems. At the end, I'm going to come back to this active community because that's an important thing. Each of these areas can be very interesting, but and one can make lots of progress in any particular one of these fields. But one of the greatest things is to be able to talk to people from other fields as well, and to be a part of a community. So, so one of the things is it brings together the different fields, and each one has very interesting, important problems from the fundamental physics, catalysis, solar energy, just many other problems, all the way to pharmaceuticals and biological applications. Now, this is a really busy slide, but it's the reason it is because I want to emphasize the range of things that's involved and the range of opportunities. So what do these fields have in common? Each one has things that are special to it, and there's just huge numbers of theoretical methods to approach them. But if we want to get one thing that's in common for all these problems, it is quantum mechanics, that the fundamental theory of all these materials is the theory of nuclei, which make the structures of the materials, together with the electrons that tell the nuclei, bind the nuclei together, and that's a quantum mechanical problem. And so therefore, we're studying the electrons. And this forms a field all by itself, the electronic structure problem. And as a field itself, it presents among the grand challenges of physics, the many-body problem. But for us, the most important thing is that there have been methods developed to treat this problem in ways that are very accurate. We don't have to be the geniuses that solve the grand challenge of physics. We can be the geniuses that attempt to solve some other problem using these methods. An important part of this is computation, because it's only because we have big computers that we can solve realistic problems. The basic theory is there, but computers are needed to make it realistic. And in addition, we can actually work with the experimentalist because it's studying real problems. People
Sorry, bro. Sorry, bro. Resume, can you mute your voice, please?
Okay, and the problems really can have significance. So now in this busy slide, there are two things that are highlighted with the square box. It's what's the topic of this workshop is computation, and the particular method is this PWF, and the density functional theory, which is the basic theory. They're the topics because they're the thing that makes all the advances feasible. And the other topics of this school are, what do we want to study? So here's the outline that I received. I'm not sure it's the absolute latest, but it's certainly the basics of this school. And I'd like to say that we started with quantum mechanics, and I believe we're going to start in a way that does not require a lot of knowledge.
نعم لدينا عملية وزارة دكتورة إسلام في
Sorry,
شركة عبد
sorry.
العزيز.
Can you please everyone try to mute themselves? Everyone, please check if you are not muted, please. Sorry, Prof. Go ahead.
It's super important to see what the problems we're going to study. And so that's the subject of I believe it's 2 days of lectures that have to do with what are the problems that we want to address. And then we get to the methods that are really used nowadays, and density functional theory is the great advance. So it's the um, the framework in which we want to approach these problems. And two other things that's on the schedule is forces and phonons, which is that the electrons tell the nuclei how to move, and they provide forces on the nuclei and move the nuclei to the structures, or determine the vibrations, which is tells you a lot about the materials. And the particular ways of calculating these are basically using density functional theory. So this whole section of the workshop is getting at the tools for what we have to work with theoretically and doing it in a practical way. And finally, whoops, oh well, okay. There's new theoretical methods and maybe I should have said computational methods that are being developed now. So that's also a part of the of the workshop and of the entire field now. So there's new work going on and there's exciting work going on, and that's the basics for this workshop. I would like to say it's a double grand challenge for this problem. The electronic structure, I've emphasized as a many-body problem, and that's one of these things that's been studied since the origins of quantum mechanics. And what we'll study is ways that you can actually do feasible work. And the importance is that the electrons determine all these properties that we've talked about in the last slide. But to be useful, it's got to be accurate. So there's two things. It's a difficult problem, and it must be solved accurately. So it's really a double problem. Why we say accurate? The difference in energy between one structure and another is really small on the scale of the total energies of the system. The ways that one distinguishes whether a system is going to be magnetic or not is really a small energy. And so you have to be accurate on a hard problem in order for it to really be useful. And then up until the 60s, there wasn't any idea for how you would actually do such accurate calculations. And so it's in 1964 was the advance that made this possible. Since I did my thesis work in the 1960s, I know that truly was this zero idea of how one could do this problem and actually come out with accurate predictions. And it really was a revolution, and that's something I wanted to emphasize, even though it may be that one can use the computational methods that have been developed now without appreciating what's going on in the past. I want to be sure that you know what's going on and what a great advance it was. So pause and think about it. The quantum many-body problem was solved, was not solved, was worked on by a host of very smart people all the way from Schrödinger to Feynman and more and other people nowadays. Nobel Prizes and Nobel Prizes and great advances. But still, there was just not even close to ideas for solving it realistically for complicated systems. Suppose that in the midst of this hard problem, someone comes along and writes down something that you can do in 1/2 a page of handwritten notes. It can be understood with anyone with a basic knowledge of quantum mechanics, and it makes possible the accurate calculations for thousands and thousands of materials. Was that worth a Nobel Prize? Which it did get, of course. So let's start. The basic quantum mechanics, this will be the start of this workshop as well, is the Schrödinger equation. There's other ways to look at quantum mechanics, so this is how not meant to be all the wonders of quantum mechanics, but it's practical ways to use quantum mechanics. And basically, the Schrödinger equation is the equation for a wave function, and it's just a differential wave equation that has a second derivative of the wave function, which is the kinetic energy and the potential energy that where the electrons are affected by other things, like for example, they're in the presence of the nuclei, and the eigenvalue is the energy that one wants to understand from the quantum mechanical equations. And I want to say that this can be written as an Hamiltonian. H times a wave function is the energy times a wave function. And the Hamiltonian is essentially an operator. It's the second derivatives and the multiplying by a potential. And the idea is this is really a soluble problem for one particle. It's either analytically, like for the hydrogen atom, or numerically by the ways that one solves differential equations. Where it gets difficult is when you have many electrons. So I want to write down a equation that's really easy to write down and really difficult to solve. It looks just like the previous Schrödinger equation, but this thing called a Hamiltonian is much more complicated. The kinetic energy is a second derivative, is a sum over each of the electrons, I should say, independently, so that's easy. You can multiply the wave function by the potential energy due to the nuclei, which is the Coulomb potential. And C is the charge of a nucleus, and it's 1 over the distance from the nucleus. That's easy. But the electron-electron interactions make it a really hard problem. It's not a sum of 1, 2, 3 electrons. It's the 1, 2, 3, 4, 5, 6 electrons all interacting with one another. So if we throw away that term, then it's essentially just the problem of each electron independently. Then the only complication is that they have to obey the exclusion principle, but that can be taken into account by matrix methods. That's quite feasible. So it's something that can be done, and so we can just simply regard this as a soluble problem. As I said before, it can be analytic in some cases, and with computers, you can solve it for many electrons, thousands. And that's what the software has been developed to do in the last 30 years or so. So now we have the software like the plane wave codes that are used in this workshop that allows you to do such calculations. There's a lot of tricks and work that's gone into that. I don't want to belittle it, but for our purposes, the main thing is that you can do it. And so let's go back to the real problem. The real problem has these electron interactions. And now it's not a problem of independent electrons, but it's a factorial problem. It's not something that's, if you have n electrons, it's not n independent electrons. It's an n factorial where each electron interacts with all the other electrons. And it's not a small effect. It's a big effect, and somehow it has to be treated accurately. And one way to say it is that the electrons are correlated. One electron depends upon the positions of all the other electrons. And in the chemistry world, there's work to solve this extremely accurately. But even with the largest computers today, you can get up to 10 or 11 or 12 electrons. And that means you can solve very small molecules, but the computers just run out of steam. There's just no way to solve large numbers of electrons, like in large molecules or in solids. So what was the development that made it possible to treat this problem for real systems? And why did it get a Nobel Prize? Because it was so useful and so ingenious. That's the word I should have used, not insightful, ingenious, because it really was. And it turns the problem around and looks at it differently. The problem is not to do an exact solution or not to approach the problems in ways that can be solved exactly, but become too hard. It's not an exact solution. It's an idea, a framework for making approximations that then really are just very, very useful. So there's still work developing the approximations. So now there's still work that's in real fundamental physics going to make these approximations better and better. But they're already at a point where you can make great progress. And that's the density functional theory. So let's look at how this came about. The first work was Hohenberg and Kohn, which is that all the properties of this complex system are determined by the density. And we'll use the symbol N for the density. And it's just a function of 3 dimensions. Even though there may be gazillion electrons, the density is just one 3-dimensional quantity. And now, does that sound like magic? How could it be that this super difficult problem is determined by just the density? I'm pausing for just a moment because it really is magic, if you want to look at it that way, how could this be true? And the answer is in 2 or 3 steps. All properties are determined by the potential. That means you just solved the Schrodinger equation. So the potential is a function of the position in 3 dimensions. That's like, for example, the potential due to the nuclei. But the only way you can do anything with it is to solve the Schrodinger equation, which you can't do for complicated systems. So what Hohenberg and Kohn showed was that the one-to-one correspondence. If you know the potential, then in principle, you can calculate the density. But similarly, the other way, if you know the density, there's only one potential that can give that density. So the potential determines, the density determines the potential, and everything is determined. And the only trouble is, this didn't get you anywhere. You're still left with the problem to solve the Schrodinger equation. It's a beautiful theorem, but it gives you no way to actually calculate anything except to go back to solve the Schrodinger equation. Oops. Well, sorry. Now, was that worth a Nobel Prize? That's part of this half a sheet of paper that I mentioned. The thing that really was worth the Nobel Prize was putting together that previous idea and constructing a system that was a soluble independent problem that has the same density as the full interacting electron problem. Now, if you have an independent electron problem, like we said before, it's soluble. And there's now software to do a lot of calculate to solve the problem for a lot of cases. And you add to that an energy that takes into account all the hard parts of the problem that you don't know. Now, this is still just writing down equations and not getting anywhere. But the idea is from the original Hohenberg and Kohn idea is that extra part, the hard part of the problem is a function of the density. If you knew the density in principle, you know that. And here was the idea that made it really, really useful. It's that you can approximate that term, and you can approximate it accurately. So we've turned the whole problem around from something that you know exactly what to do, but you can't do it, to something that you have a picture in which you approximate the hard parts of the problem, and it turns out that the approximations can be exceedingly good, and you can understand the basics of the approximations, and there's more and more work that's to improve it and improve it. So, how good? The local density approximation is just uses information from a homogeneous system of electrons that we know a lot about from calculations of that problem, and applying it to other things like atoms and molecules. And it's actually very good. So already in 1964, the most useful, I shouldn't say most, excuse me, the basic approximation was given, and from then on, it's been improved, and part of the improvements is what will be part of this workshop. And it's been really useful. The first step that showed it was useful is that you could predict the lattice constants of crystals with astounding accuracy, like 1%. You could predict how the atoms would vibrate, like a few percent accuracy. You could get the structures of molecules. That's the structures that may have little tiny energy differences, but you can predict it accurately. And so it's just useful. So it turns out that then, because it's so useful, the Kohn-Sham papers are the most widely cited papers in physics. And it's really transformed how research is done. Can you believe? I still find it hard to believe these numbers, but it's actually accurate that based on real counts of papers, like 10 years ago, there was about 30,000 papers a year, and certainly now is 50,000. I can't even imagine 50,000 papers, period, in all fields, but there's the density functional theory is so useful that it's widespread this much. I've done a little survey to myself just to see, well, now how useful is it just to see what are examples? So I've looked at Science Magazine, which is the main journal in the United States that covers all fields of science. And what I found in a few issues when I made a little study last year was that for 3 issues, I found 5 papers that reported work on the atomic scale. This is out of all the papers in those 3 issues of Science. There were 5 papers that started with quantum mechanics and really on the quantum mechanical scale, looking at materials from molecules to solids. All of them were experimental papers. None of them were particularly oriented toward theory, but every one of them used DFT as part of the research. And in every survey I've done in recent years, DFT was at least an integral part of half of the experimental papers. Sorry. And here's just one example. This was one of those surprises to me. Here's work that's practical work and attempting to make efficient perovskite solar cells. If you look at the abstract, you say one of the primary challenges is in commercializing perovskite cells is achieving high efficiency while being stable. Stability is the key issue for these perovskite solar cells. That's so much a part of research nowadays because they're efficient. And look in the text. We perform first principles density functional calculations to investigate phase transitions, which is what happens at this particular research that these people were doing for trying to make them more stable. So that's just one example. So they're amazingly good for many properties, but the other thing that this workshop should do is tell you it doesn't do everything. There's some things that are just not supposed to be done well by this formulation. Things that are different from total energies and structures. And there's lots of interesting work going on to study these properties, and lots of work going on to improve the density functional theory to do a better job of these properties. But don't expect it to do everything, and be aware. It's a great advance and it's extremely useful, but it's very important to know how to use it and how to avoid problems, how to avoid making problems yourself, how to avoid errors. So something that's really important, but it's really important to know how to use it and how not to use it. So let's pause again after all this stuff about how useful and the tools that we can use and the exact things that a scientist needs, and think about that you really have to have a background. You have to know some of the basic theory and some of the facts of the problems that you want to deal with. And you need to have the tools. Computational work, that of course means computation. That's the subject of this workshop up to a point. You just have to do that if you want to do research. But what else? You need a community. This is not the type of problem that you work on in isolation. You need colleagues to discuss with. You need local networks for collaborations and stimulating ideas. You need connections to the global science community. That's where you find out what's state of the art and what's going on nowadays, what's worth doing, where can you do work that will make a big difference. And one of the great things about our field is that a community has been built up for computational material science, in particular at the quantum level, using density functional theory. So I'll mention two areas that I think are especially show how one builds up a community and how one can be a part of a community. I've been involved in ASESMA, that's the African School of Electronic Structure and Math and Applications, for 18 years now, and it's built up a community. Another example is a cartoon workshop on advances in material science, which has been a wonderful series. And well, it's so sad what's happened more recently in Sudan, but you people are still there, and you can be part of a community even though it's difficult to carry on the science right now. So here's about ASESMA. This is the school that's been going on since 2008 and most recently in Ghana in 2025. And it's led to a community and given the name ASESMA Galaxy. The schools, the next one will be in Senegal in 2027. There's a whole set of regional schools that's going on that are smaller and more dedicated to particular aspects and can be done. And it's the kind of local networks that one needs to have. The AssessmentNet is a program to provide more opportunities for collaborations within Africa and travel to conferences in Africa and outside. And now it's built up a large number of active research groups that's shown by these, well, the countries is shown by the dots. In many countries, there are quite a few research groups, like in Ghana, Nigeria, Ethiopia, Sudan, South Africa is a particular example of a very large number of groups in which people from the rest of Africa, often the students and so South Africa is very important for nurturing the science in the rest of Africa. So I want to end with emphasizing that working together is really important. Building a community and being part of a community. So I really want to encourage you that this is a field where there's really interesting science work and interesting work that can lead to technology, and you can be part of a network, part of a group of people that extends from your local colleagues at your university and your local group for which you can have discussions and on the internet and as well and be part of the global science community. So best wishes for a great workshop and thanks to all the people who have put this workshop together. I'm going to put this back up just so you have it. Thank you. That's it.
Ala, go ahead.
Thank you so much, Professor. It was an honor, a very nice lecture. And now we take questions. If you have a question, you can open your mic and ask your question, please.
Hello,
Hello?
can you
This,
hear me?
yes. Is this
Okay.
Musa?
Yes.
Yeah,
Okay.
thank you very much, bro, for this talk. It was really refreshing, especially for me. Yeah, and this is really interesting. And one of the things that actually I wanted to mention about this, Richard actually one of the first people that when I met earlier at Berkeley, we had a conference together, and when I talked to him about this workshop, he was so excited. Yeah, this is a really good idea, and let us do it. And he's been always like encouraging and supporting this kind of initiatives in Africa.
Yeah.
And thank you for that, Richard. And it is a great honor and pleasure to having you today, kicking off our workshops. Um, so the other thing that actually I have two questions, but before going to my questions, I want to emphasize that because I put some resources in the WhatsApp group for this workshop about the Assessma website and then Assessma GitHub. Feel free to use all of these resources, digging into the website of Assessma and try to apply for Assessma Senegal 2027. Just watch out and look up into the website and try to apply. I'm pretty sure after this workshop, you are going to get the basics of the theory and how to run simple calculations. This is going to help you a lot, even when you apply for a big assessment in Senegal. And also, one of the things that I want to mention, Richard Martin is the father of assessment or father of electronic structure in Africa. So thank you for that, for bringing all of these things together to Africa and try to help African scientists to grow. Yeah. So my first question actually is about functional and exact functional. I'm not following actually the research in these directions. Is there any progress people are doing right now toward this finding like the exact functionals, or people they just stop there and using these exchange correlation functionals to handle different systems? This is my first questions. My second question about AI. Nowadays, everybody is talking about AI, machine learning stuff. Do you
Yeah.
think AI can help us to overcome this challenging, or people is still some sort of skeptical of using AI?
Okay, so first of all, there's a lot of people who have been important for the electronic structure world in Africa, and so I want to be sure they get credit. The first people who started assessment was Nithya Chetty, who was in South Africa, um, Sandro Scandalo, who's at ICTP, and others. I want to mention Daniel Joubert in South Africa, who is now retired. But there's others that were sort of behind the scene, and ICTP is just totally important in making this work out. So we need to give credit to the other people. The second one is about functionals. The I think the it's almost like the world that we're involved in has divided into people who really cared about the functionals, what can be exact, what's not exact, and that's almost a world in itself of what's a functional of what. And so I would encourage you to think of it as as if you're really interested in things like that, then go for it. And if you're less interested in getting the exact, whether or not there exists an exact functional, then you can look at what is being done to make better and better functionals. And there you find that in order to make a better functional, you have to deal with that grand problem of the interacting electrons. And so that's the kind of thing that's been going on now for ever since density functional started in the 1960s. So that's one of these places that it touches fundamental physics. Um, the the and so that's always working in the framework that we know it's approximate. We just want to make it better. Now, what about AI? I am not an expert on AI. That's something for you younger people to really do something with. But it's very clear that it's one of the ways of approaching the problems that's going to be important and making better and better functionals, but then also better and better methods to uh, to use the work that other people have done to do better and better applications to more and more difficult systems, or be more and more realistic for how complicated systems can work. So AI and machine learning are two things that are just guaranteed to be important for the future. So please keep your eyes and ears open for things like that.
Thank you very much, Professor Martin. Now we take another question from the participants. If you have any question, you can open your mic and ask your question. Any question? Don't hesitate, please.
Yeah.
You can also type it in the chat, yeah.
As people tell me, there's no such thing as a dumb question. If something is not clear, or you just wish to ask about something that might be of interest, then it's likely to be interesting to someone else too. So please.
So
Yes, Musa, do you have another question?
yeah, I mean, like, while people try to figure out questions, maybe. So what is your advice, Richard, for the beginner in this field?
Okay, for the beginner in the field, be aware that there's things that have been developed over the past 30 years with where you can use computers, and you can do a calculation on a system with a laptop with only a little bit of information, a little bit of background. And if you're an experimentalist, so you want to talk to an experimentalist, there's you can do work like that, but be aware, most of all, that you need to be you need to understand what you're doing, and that's where it's more than just turning out a calculation. Being aware of what are good problems to work on, and where these calculations can be believed, and where one has to be very, very careful whether they're accurate enough for the problem that you're interested in. There's a lot of poor quality papers, and to some extent our field has a bad reputation because it's relatively easy to do calculations on complex systems, but if it's done without knowledge, without care, without knowing where one can make mistakes, that then you're not contributing to the science community of our global science community. So being aware and understanding what you're doing is just totally important. So listen to the all the lectures of this workshop and look for the advice for how to use these methods well. That's my biggest advice for people beginning in the field.
Thank you very much, Professor Richard, for the advice. And again, for the participants, we have a question from Sahar in the chat. She's asking, do you think the explosion in DFT studies lead to the retardedness of experimental research and become less important to researchers? So just to explain more, she's asking if the studies using computational methods led to less experiments.
Oh, that's a good question.
Yes, that's really good question. So
okay, so that's a great question. It should lead to more experiments, and not less experiments. It just leads to better experiments. There's I've actually made jokes and I've had a talk about when can we do without experimentalists, and but that's not the point. The point is working together and learning how to do better experiments, learning how to use ideas that come from theory to suggest what's a better experiment to do. I'd like to take two examples. One is a very general, generic example that that is that just for what experiments can do and cannot do. Uh, Consider a nanostructure, something not a perfect crystal like silicon. For perfect crystal like silicon, you believe experiment. You know what's the band gap. You know what's the lattice constant. It's just done. And you use that to test the theory. How good is the theory? But when you get to a nanostructure, the experimentalists don't know where the atoms are. And they don't have a method of saying that we know that this is the exact structure or not. We don't know whether these atoms on the surface of the nanostructure have this structure or that structure. We don't know a huge number of things that theory can help. So if we're really careful with the theory and know how to apply it, and when we expect it to be accurate enough, then we can contribute a huge amount to the experimental work, and can help experimentalists grow new nanostructures and test them and do new experiments on them, et cetera, and do more and learn more. The specific case was the one that I showed as part of this talk. Let's see. Hope I can find it without that one. Is this case was a proposal? It's not a proven thing. Proposal that you could enhance the stability by incorporating different materials on the surface of the perovskite. But what's required is to know how this material bonds to the perovskite. And and so it's something on top that's supposed to protect it, but it works only if you can have it both join the perovskite, bond to it strongly, but not affect its properties that are so good for being a solar cell. And that's where it came in, this density functional calculation of the phase that's right at this interface between this coating and the perovskite, where the experimentalist simply doesn't know where the atoms are. So just an example.
Thank you very much, Professor Richard. I would also emphasize on this question. For me, as an experimentalist, I grow 2D materials in the lab on different substrate transition metals. So I do the theory, the DFT calculation, just to find out if the HPN, for example, hexagonal boron nitride, will grow
Yeah.
on nickel or platinum, which one is perfect. This guide me for the experiment and also minimize the time that I will take in the lab. So yes, DFT is mainly to guide the experimentalist. Exactly. Thank you so much, Professor.
Oh,
And
thank you for your example. That's great. And
Yeah.
can you give me an example where it might go wrong? And will you have to be
yes,
real
yes.
careful?
Yes, it might go wrong. Yes, because also for the experiment, we control the conditions to some degree, but growing 2D materials in ultra high vacuum, study them with different techniques it takes time. And also the theory sometimes is not accurate enough to predict.
Right. So it requires working together with and learning from other people where things would be accurate or not accurate. It's really uh, being part of the community is very important, and knowing what's going on is very important.
Yes.
Okay, excuse me for interrupting.
No, thank you so much, Professor. And we go to the participant. If you have a question, you can write it. We can take another two questions from the participants just to close. We have a hand raising. Noon Al-Agib. Yes, you can unmute yourself and ask your question. Noon?
Thank you, Prof. Richard, for this nice talk. My question is, how do you decide whether the DFT is the right method for a research problem before starting the calculation?
Oh, but actually, you won't know exactly whether it's the right method, but you can get a lot of ideas from experience. When you have something that's an approximate method and you want to apply it to a very complex problem, and almost every problem we have is complex because it involves structures of systems that not just the very simple molecules and atoms. So almost every problem is complex. So experience and paying attention to what's actually been done before is by far the most useful thing. Let me just take an example. Um, we can we can predict the positions of the atoms in many systems, but whether it will be magnetic or not, for example, is something that's really pretty delicate for for many systems. Uh, it's it Iron is magnetic. Um, no, I should take it back. Nickel, you can find almost, it's a very solid system. You pretty well know what's going on. Iron and its various structures can be magnetic or not. And there's actually mistakes, so like 30 years ago, uh, of where predicting iron to be non-magnetic, and but mistakes that were done honestly. And in some cases, it's very important to do something honestly and get the wrong answer. because now you've learned something. You do a good calculation, and you've learned that this aspect of density functional theory is not good enough. That's very, very important. So doing honest calculations is very important, and learning from other people's experience and reading the literature to get an idea of whether or not this problem that you want to approach is one that you should approach using these methods is I don't know of any other way other than learning from what's been done by other people. So good luck with that. And I didn't mean good luck. And excuse me. Try it, and you will find it rewarding.
Thank you, Professor Richard. We have two. We take one question from Nihat and then from Musa, and then we close. And Nihat, please unmute yourself and ask your question. Introduce yourself first.
Hello, my name is Nihad Omar, and I am assistant professor in Sudan University of Science and Technology. First, thank you, Professor Richard, for your valuable presentation. I just want to ask that is DFT applicable for all types of solids? For example, disorder solids, which have some degree of randomness in arrangement of atoms, like high entropy alloy. Is it able to simulate these types of solids?
What was the last word you said? Is it able to simulate what?
Disorder solids.
Oh, disorder. Oh, now we're at the theoretical levels. If you have a perfect crystal or a finite nanostructure that you can deal with the whole thing, then you pretty well know what to do with the methods. If you have a disordered system, then you need to add extra ideas to do it accurately, because you want to do a piece of a large system that's not ordered, and so there are ideas that treat it as a large as a crystal in some sense, or as a body embedded in the rest of this disordered system. So now you're at a different level where some other aspects of theory are needed in order to even set up the problem properly. But again, it's an interesting problem, and there's some very good work that helps you get started in that approach and that attacking such problems as that.
Thank you, Prof.
Thank you so much, Prof. And now we have a question from Musa. Musa,
actually, I don't have a questions. I just want to comment. Okay. I have some comments on these questions. Actually, they are really interesting. Sahar, Noon, and Nihad, these questions are really interesting. So my first comment on the experimental side, the best thing that like nowadays I have seen a lot of published paper, they combine both like theory and experiment. They have DFT and they have some experimental also measurement. And myself, I started also involving in a project. The project start like as a very simple request from experimentalists. Hey, we are growing this phase. Can you please do DFT calculation for this and tell us like which phase that we are growing? And then I said, okay, let's do it. And this project has been going more than 2 years. So like so in each meeting, so we speak a different language, but I have my feedback, they have their feedback until we reach to the point, okay, this is the phase that we agree. So nowadays people, they really work close to each other, like experiment and computational physicists together to find something really, really important. My second comment on the disordered systems. During my PhD, I worked purely on the crystalline, and during the postdoc now I moved from crystalline to non-crystalline, which including amorphous material or disordered systems. And also in literature, people when they say disorder, there are different level of disorder. There is doping people, the defect people, they call it disorder, and there is this amorphous people, they also call it disorder, where you have no translation symmetry in your system. So, and I totally also agree, people, they try also to make like a new theory actually to understand this level of disorder. But disorder term itself is a really big thing. In principle, you could use DFT to simulate any kind of solid, but you have to be very, very careful on the way that you treat your systems. And I always recommend check literature. Maybe some people, they have done this kind of things like long time ago, or like they are trying to do something, or they reach to the point that this is not gonna be easy, or they stopped at some point. So it is always better to check literature if you're starting anything new. Yeah, this is my comment. Thank you.
Oh, perfect. A nice example and personal testament for what you have done and what you think is good to do. And I just want to second what you said, and emphasize even more how useful it is, and how essential it is to read the literature and keep up with what's been done and what's going on now for understanding where things are can be trusted and where one has to be very, very careful, and what's interesting at the present time. So thank you for what you said.
Thank you very much, Professor Richard. We have the last question written in the chat by Potaiba. He's asking, how can a ground state theory like DFT be consistently combined with methods that describe excited states or higher energy physics?
Oh, okay. So I think number one, if coming from the problems of solids or materials or molecules, the ground state determines the structure, and you just have to have that right in order to go to the excited states. Because it's how the electrons are bonded together in the ground state is the starting point. And now you want to look at something like optical properties. How is the light absorbed or it emitted, or if you what happens when it's radiated, when there's irradiation of various forms, then you just simply need to sometimes go to different approaches. Sometimes you can understand how to extend the density functional in practical ways, but recognize that it really is a different problem, and requires different sets of approaches to figure out what's needed. So care and looking for experience is, I think, by far how you determine what what should be done or what problems to choose.
Thank you very much, Professor Richard Martin, for the nice lecture and for the advices you have given to the participants. And thank you, the participants and everyone. And this is the end of our lecture today. Thank you.
Okay. Can I add one more thing?
Yes, please.
I want to thank again the organizers for this workshop, and I want the people of Sudan to know that the people in the rest of the world care about you. I'm honored to be part of this, and want to stay in touch with you as well as I can, and help advance not only science but society in Sudan and other places. So um, I just want to say that, to encourage you in the face of great difficulties.
Thanks
Thank
a lot.
you so much, Professor.
Yeah, that means a lot for us. Here is Abu Bakr in behalf of the organizing committee and Photon Center, which is the part organizing the workshop with the ICTP Physics Without Frontier. Thanks a lot. It was very detailed and inspiring lectures. And thanks also for this encouraging message, Prof. We really appreciate that. And also I would like to thank all the participants for their great questions and all the other organizing members. We will meet tomorrow for all the participants, as we mentioned, as we did outlined in the schedule of the workshop, and I will communicate with you the Zoom links, whether via email or via our WhatsApp community. So thanks a lot. Have a good day.
Best wishes.
Thank you all.
Bye bye.